Alright, Year 11, new chapter, all on energy changes in chemical reactions. So our inquiry question is, what energy changes occur in chemical reactions? Nice and simple and straightforward there. Okay, there's the syllabus points, and underneath I've written, we have already seen that one sign of chemical change is temperature change of the surroundings, okay? Either the reaction has consumed energy or it has released energy, okay? So how and why these changes occur is called thermodynamics, or when we apply it to chemistry, we call it thermochemistry. So investigating how energy transfers in reactions is a connection to why reactions happen. Okay, it's leading us to the end of this module, why chemical reactions happen. And sometimes don't. I like that too. And it gives us a great insight to how the universe works as well. Okay, so first up, some new words, system and surroundings. Okay, when we talk about energy transfers, we use the term system and surroundings to describe the environment and where the reaction happens, okay? So the system, when we're talking chemistry, is the particles that take place in the chemical or the physical change, okay? So the actual particles that are undergoing rearrangement of bonds, or the particles that are moving apart from each other and doing funny things to do physical changes. Okay, the surroundings is just the environment around it. So anything right next to it, another molecule, all the way out to, half a meter away, 1 meter away. Okay, so it's very broad, the surroundings. Okay, so here I've just drawn a diagram. It's going to help me explain it, but I've got the system there in the red dot and the surroundings around it. Okay. So for an exothermic reaction, exothermic reactions are detected when the surroundings increase temperature, okay? So the temperature increases in the surroundings, okay? Capital T, big capital T. So that means energy has come out of the system into the surroundings, okay? If energy has left the system, the system has lost energy, and the products now sit at a lower energy, okay? So energy's moved from the system and moved to the surroundings. The system has decreased in energy, okay? So here with an energy diagram, and we started to see these last chapter, we have the progress of the reaction down here. So our reactants were somewhere up here, and they went through an energy barrier, and now the products are down here at some lower energy, and there's this energy difference here that's represented, okay, between the start and end. There's also this activation energy, and remember we talked about how to change that, but here we're focusing on this thing here, and we'll talk about more about these symbols in a second. The energy that's left over is coming into the environment is usually heat, sometimes light, okay? That energy that has come out is the difference in the bond energies between the reactants and the products. Okay, the other type of energy is endothermic. Or, sorry, not the other type. The other type of reaction. All right, so here the system is gaining energy from the surroundings. So endothermic reactions are detected. We see that in our everyday life when the surrounding temperature decreases or it gets colder. Okay, so energy has come from the surroundings into the system, and that has occurred because the reactants are at a lower energy than the products. So as the reaction proceeds, the system needs a certain energy to reach the products. Okay, so it takes that energy from its surroundings, so we see that as cold. So notice here, this is a positive difference in energy. Okay, so the energy comes from just temperature and stuff around it, so taking energy from molecules around it, so they're not wiggling as much, they're not moving as much, they're not bending and stretching as much, and that energy goes into the system and it goes into the molecules to form new bonds. Okay, so back into potential energy there. Okay, all right. So one thing I'm going to point out, notice how here, exothermic, the difference is as it goes along, goes down, it goes negative, the energy. And here, the energy difference is positive. It goes up through the course of the reaction. It goes positive. All right. Here it goes negative. Those signs will carry through when we start to quantify these energy changes. Okay. One thing that I need to add in too, we're considering the system and the surroundings are in contact. So, and we'll be talking about other things where hot things and cold things come together. And remember then, I think it's called, is it the first law of thermodynamics or the zeroth, which we don't need to learn, but this is very handy. Two objects that come into contact will tend to reach thermal equilibrium, or they'll balance their temperatures out. So if you have a cold object and you put a hot object in contact, heat will flow from the hot part to the cold part. Okay, that energy will be transferred along through conductivity. So all those wiggles and stuff like that will all be transferred until they're evened out throughout the two objects that are in contact until they're the same temperature. Okay, the amount of heat energy in a substance depends upon its temperature, the amount of matter it is, okay, and also a certain other property that we call the specific heat capacity, okay? So you can have the same amount of the same amount of energy in two objects, but they feel different temperatures because one is bigger than the other, okay? So it depends on how much stuff is there. So heat energy, how much stuff is there, and another certain property called a specific heat capacity, which each different material in the universe has a different specific heat capacity. I really like this video, a Veritasium one. It's very good, and it explains more about this specific heat capacity and our misconceptions about temperature. It's a very good video. Okay, so here's a little thought experiment. I've got these two pots over a fire, and this fire provides these two pots with 100 joules. Which one of these is hotter, the metal pan or the clay pot? Now, intuitively, you might have a bit of understanding to this too, okay? We know that metals have this special property with heat, and we often cook with metals, okay? And so, metals get hotter than other materials in general with the same energies. So metals absorb and dissipate heat more easily than other materials. Okay, so we have heat conductors and heat insulators, which we learnt about in year 8 and 9. So when we want to cook something fast, we tend to use metals as they don't need much energy to change their temperature. Clays and ceramics and other materials take a lot more energy to change their temperature. Okay, so both of these are good cooking vessels, but usually your clays and stuff, they're slower cooking methods. Okay, so they're used for slower cooking methods and distribute heat evenly throughout what you're cooking, whereas the metal just applies it very quickly for cooking methods, for fast cooking stuff, so like frying an egg or something like that, not making a stew. Okay, so these properties of material to absorb and dissipate heat quickly or slowly with different amount of energy helps us in everyday life. Another thought experiment I thought I'd put in is, here your car runs out of petrol and you have no shoes. How do you walk to the next town? Do you walk down the middle of this bitumen road? Do you walk down the edge? Do you walk on the grass? Do you walk on the white lines? I mean, you can pretty much think about it there, can't you? This looks rather technical, but this is another kind of thing about heat absorption and dissipation here. I've got 4 kind of graphs, and what I'm talking about here is temperature over time. You'll notice here I've got temperature and a date. It's a pool, daily maximum air water temperature, okay? So the pool temperature is the green dots. Okay, and you can see that fluctuates a little bit, and the air temperature is the red dots, and you can see that fluctuates quite a lot. It's, hot, cold, or day, night kind of thing. And you can see that, might be able to see that the peaks are slightly offset. Okay, peaks are slightly offset. And that's what I'm getting at here too. So what have I got here? Time, hours. So I've got a 25-hour period of temperature of, it looks like temperature of air versus temperature of sea. Okay, and you can see that, well, there's a minimum there for the air, and there's not really too much. It's not the best graph, but there's a minimum down here too. Probably not the best graph to demonstrate my point. Okay, temperature air, temperature soil. Notice that the maximum temperature air is here, and temperature soil is here. Temperature, maximum temperature there. There's a lag time, okay? And here we've got talking about a temperature lag. We've got daily temperature, energy rate of a day. Okay. So we've got a maximum here at 4 p.m. of a daily temperature and a minimum at 6. All right. Incoming solar energy, the maximum is there. Okay, what I'm trying to hint at is different material absorbs heat at different rates. Okay, and so the hottest part of the air may take time to heat up other materials too, depending how good a conductor that is and a good absorber that land is, or something like that. So in natural systems where you get fluctuations in temperature, so day-night cycles or winter-summer cycles, you get a lag between, say, the water temperature versus air temperature, or the air temperature versus land temperature too, because it takes time to transfer that energy, okay? Water's a really good heat insulator. So is land's not as good, but a decent amount too. So you get these lags. Some other applications, we can think about how a heat sink works, and you can watch that video, okay? And made of metal, large surface area. And also these materials here that I've got 2 videos on the ceramic tiles that were used on space shuttles, and are probably starting to be used, similar technology, on the new reusable space shuttles used by, well, not shuttles, but like the Virgin Galactic and SpaceX technology and stuff. So there are all these materials here that can absorb a lot of heat but not change temperature and not get hot, okay? But can absorb a lot of heat. So you'll see that someone picks up one of these glowing things because it doesn't transfer energy very well at all. Okay, this measure of how things absorb heat is called specific heat capacity. Okay, and it tells us how much energy it takes to change a mass of the substance by a certain amount of degrees. Okay, Kelvin or Celsius. Okay, because remember, we're talking about a temperature change, not an absolute temperature. And remember that the magnitude of a degree Kelvin is the same as a magnitude of a degree Celsius. So when we're talking about a change in temperature in Kelvin or Celsius, they're equal. Okay. Now, this specific heat capacity is a number, and we're going to use the units, usually joules per gram per Kelvin. That's what chemists tend to use, okay? So how many joules does it take to change 1 gram by 1 Kelvin, okay? So it takes that many joules to heat 1 gram of the substance by 1 degree, okay? And here I've got a table, and I'm asking you, what trends do you see in the table of specific heat capacities, okay? I've put them in numerical order. I was going to say chronological. Excuse me. Largest up the top, smallest down the bottom, okay? So here we're saying that for helium, it takes 5.193 joules to heat 1 gram by 1 degree Celsius or Kelvin. Okay, so every So if you've got a larger mass, you just multiply it out by the mass, or if you want to change it by more than 1 degree Kelvin, you multiply it out by that, okay? So 5.193 for helium, and then we move down to ammonia, and then water there, 4.181 joules per gram per Kelvin. I liked seeing this value, I found it somewhere, so animal tissue, roughly, around 3.5 joules per gram per Kelvin. And then we're moving down through ethanol. Notice that ice, change of state of water, it also changes the specific heat capacity. Then we've got neon, magnesium, first metal that we're seeing. We've got air, and then aluminium, second metal. And then you've got some concrete, glass, diamond, and then iron, copper, mercury, lead, gold, uranium, all metals down the bottom, okay? So the general trends that you should be seeing is that non-metals tend to have large specific heat capacities, okay? They take a lot of energy to change its temperature. Metals do not need a lot of energy to change its temperature, okay? They tend to be down the bottom of the scale there. Okay, one past paper question and one Mr. Roberts question. Let's see how we go. What is the specific heat of a compound? So it's going back to that definition that we just learnt. The quantity of heat required to boil 1 gram of the compound. No, we're not talking about boiling. We're just talking about changing the temperature. The quantity of heat required to melt. No, we're not talking about a change in state as well. The quantity of heat required to increase the temperature of the compound by 1 degree Celsius. Yeah, kind of, but it's missing something, okay? The quantity of heat required to increase the temperature of 1 gram of the compound by 1 degree Celsius. D is taking into account the amount of the substance. So C was wrong because it doesn't take into account the amount. D is the right answer because it takes into account the mass and the change in temperature. Okay? Which of the following is the best heat insulator? Or you can reword that question. Which of the following has the lowest specific heat capacity? Remember our trends. Non-metals have high specific heat capacities, and metals have the low specific heat capacities. So the best insulator is going to be, I'm going to be looking for non-metals here, okay? And look, this is nice and obvious because we've got chromium, which wasn't on our list, but we're like, chromium's a metal. Copper, mercury, metal, metal, non-metal with water, metal. Cross out all the metals. The best heat insulator is water, okay? Best heat conductors are the metals. All right. So we can go further now that we've got a specific heat capacity, and we can work out, we can use it to connect the amount of energy going into a material and the mass and the temperature change, okay? So we can put it in this formula here. It's a formula that we'll use a bit. Q here equals mc delta T, where Q is the amount of heat or energy, okay, that's being transferred, and we'll use the SI unit of joules, or sometimes we'll use kilojoules in there, but you know, that's easy to transfer between the two. M is the mass of the object, okay? It can be in grams or kilograms, but what we need it to do is we need it to cancel with the unit in the specific heat capacity, okay? We tend to use grams as chemists, though. Delta T is the change in temperature resulting from the heat, or gain in heat or loss of heat. It's always the final temperature versus the initial temperature, okay? Remember, since the magnitude of Celsius and Kelvin scales are identical, you don't need to convert Celsius over to Kelvin, okay? Just put the two Celsiuses in and find the difference. Okay, so sometimes this formula, we commonly call it Q equals MCAT. Why am I laughing so hard about that? But that might help you remember, okay? Q equals MCAT. The capital C is the specific heat capacity. Why didn't I put it in there? So capital C is the specific heat capacity for the object that you're talking about, okay? So if heat is lost for a system, we use a negative sign. Okay. If heat is gained by the system, or it's an endothermic process, we use a positive sign there. But using this delta T will get you the right sign anyway. Okay. Let's do some examples using this formula. How much heat is required to change the temperature of our 30.2 gram block of iron from 18 degrees Celsius to 45.0 degrees Celsius? And here we're given the specific heat capacity of iron. Okay, so I'm going to write my Q equals MCAT formula. How much heat is required? Well, Q is our question mark. Our mass given in the question is 30.2 grams of iron. Yeah, so just keeping track. So we're looking for C, the specific heat capacity of iron, and it's given as 0.450 joules per gram per Kelvin. I'll write it like that. And we need a delta T. So delta T equals T final minus T initial, which equals 45 was the final, 45.0 minus 18.0 degrees Celsius, or I'm just going to say it because the magnitudes are equal, Kelvin. Okay. So I'm going to work out my delta T, 45 minus 18. I'll put it in my calculator, which is really lame, but it's 27 Kelvin difference. Okay. Now let's make sure all of our units will cancel. Okay. So I'm going to say Q equals, what have I got? Mass in grams. And I'm going to multiply it by the specific heat capacity. And I've got my from my question here, joules per gram per Kelvin. And I'm going to multiply it by the temperature change in Kelvin. All right, let's track our units and make sure they cancel. Okay, grams up the top, grams down the bottom. So they cancel. Kelvin down the bottom and Kelvin at the top there. And I'm just left with joules, which is the unit that I'm looking for. Okay, I'm all good there. Now I did that because sometimes the heat capacity might be given in joules per kilogram per Kelvin or kilojoules per gram per Kelvin or any kind of variation there. Sometimes our mass in our question could be given in kilograms too. So you've really got to keep track of your units here. And because these questions are quite simple once you get to an exam, there's tend to be that type of thing thrown in. Oh, let's give the mass in kilograms, or let's give the specific heat capacity in something different so it doesn't align up, and recognize that a student can change that. Okay, so don't be tripped up. But here I've just given it in a straightforward way. Okay, so now we know it's all going to work. So we've got grams, we've got 30.2 grams of iron multiplied by 0.450 joules per gram per Kelvin, and multiply it by the 27 Kelvin. I know it's all going to work out, so I can put my numbers in my calculator now. 30.2 times 0.450 times 27, and I'm going to get my answer in joules. I get 366.93 joules. Significant figures. I've got 3 there, and I should have. What a duffer. I should have held on to the 0 there of my tenths in my Kelvin. So I can report it to 3 sig figs. So I've got 367 joules to 3 sig figs. All right. Nice straightforward problem. It's with the formula as it is. Let's do a different example. Determine the final temperature of 100 ml of water if its initial temperature is 12.5 degrees Celsius and 13.7 kilojoules of heat is applied. The specific heat capacity of water is 4.181 times 10 to the 3 joules per kilogram per Kelvin. Notice that the specific heat capacity units have changed, joules per kilogram per Kelvin. And on our data sheet that we're given in our exams and all the time that we have handy, it's got the water, it's the specific heat capacity of water there, but they've listed it as joules per kilogram per Kelvin. Just to be annoying. Okay, so we're still using, I still recognize that we're still using a Q equals MCAT formula. But I'm going to have to rearrange it, okay? Determine the final temperature. Well, I need to put delta T as the subject. So delta T equals Q on MC. Just rearranging it, okay? Now I can expand it out, but what I might do is just resolve Q equals MC first. And what I'm going to do is make sure my units are cancelling too, okay? So Q, well, I'll put out Q here equals 13.7 kilojoules. Okay. M equals, what mass have we got? Look what I've done. 100.0 mil of water. So I'm going to assume that it's 25 degrees Celsius, etc. And just put that as 100.0 grams. Okay, because I know the density of water there. C. The specific heat capacity is given in 4.181 times 10 to the 3 joules per kilogram per Kelvin. Okay. Now here I've got a dilemma, because you can see my units are not going to cancel. Okay. Kilograms down the bottom, grams at the top. Joules and kilojoules there in my heat. The easiest thing to do here is to convert the single units rather than the compound unit of the specific heat capacity, okay? So I'm going to change my Q into joules so it cancels with my specific heat capacity. So it's going to be 13,700 joules. Okay? And I'm not going to change the kilograms on my specific heat capacity. I'm going to change my mass into kilograms, which is going to be 1.000 kg. That's the easiest way, okay? So let's start putting it in, okay? So my Q in joules is 13,700 joules divided by my mass in kilograms, 0.1000 kilograms, times it by my specific heat capacity, 4.181 times 10 to the 3 joules per kilogram per Kelvin. Okay, check my units are going to cancel. Joules at the top and bottom of that one. Kilograms at the top and bottom of this one. So I'll be left with Kelvin Kelvin on the top will transfer up there because it's on the bottom of the fraction. Hate it when it does that. So that's good. So I'm getting my delta T in Kelvin. So I'm doing the right thing. I'll put my numbers in my calculator. 13,700. Okay. Divided by 0.1. Divided by 4.181 times 10 to the 3. Okay, I get 32.76728 Kelvin. Okay. This is not our final answer. We've just found delta T. And it's saying find the final temperature. Okay? Now be careful here, because what we need to do is read the question. The initial temperature is 12.5 degrees Celsius, and don't presume that the temperature change is positive. It could be negative, but let's read the words around it. Okay? 13.7 kilojoules of heat is applied. Okay, we're applying heat. Okay, we're inputting energy there, so the temperature is going to go up. And the delta T is 32.76. So delta T equals temperature initial, or temperature final minus temperature initial. Okay, so therefore temperature final equals delta T plus temperature initial. Okay, so we've got temperature initial 12.5 Celsius. Okay, I'm going to have to convert back. And we're going to add on 32.767 Kelvin. That's okay. The magnitude is fine. We're going to add it on. Okay, so I'm going to add plus 12.5. And I can report that, okay, I knew the 12.5 to the tenths. So I can report this answer to the tenths because I'm adding or subtracting. So 45.267 is going to be 45.3 degrees Celsius. Okay. To 1 decimal place. 1 decimal place. All right. Oh, look, always on our data sheet. See, the specific heat capacity is always there, but they've given it to us in joules per kilogram per Kelvin. All right, you've got enough knowledge to do this worksheet when you get a chance. And if you need some more help, there's some examples from the textbook.